Hello, everyone. Thank you for joining us for this ElasticON session. Um, and we hope our subject will be interesting because we have two main characteristics of this Elasticsearch use case. First of all, it's related to the data model that we use for this project, and secondly, because Elasticsearch turned out to be a good choice for the performance that we had in using our volume of data. So let's see searching through large graphs at scale using Elasticsearch. I will take just a short moment to introduce ourselves. We are part of a small team of search enthusiasts called Adelean. We are based in France, in Paris area. We are experts in search technologies, integrators of Elasticsearch and Solar. And we provide consultancy services and training around these technologies, and we are also developers of a search engine technology for e-commerce and enterprise search, which is called A2. I'm Radu Pop. I'm a solution architect in Adelean. I'm handling project around ELK stack, about A2 search solution, and my main interest is related to the relevance in search. But for this talk, I will wear a second hat, which is a search consultant in INA team as Elasticsearch expert in data lake project.
Hello everyone, I'm Pietro Mele and I'm a junior software engineer at Adelean. I have a passion for technology and its application in solving real-world problems, and recently I've entered the world of Elastic and its stack. One of the main projects I've been working with the Adelean team is Soul.site, which is our collaborative search engine. In addition to this, I enjoy exploring the fields of machine learning and computer vision. As a search consultant at the INA, I bring additional expertise in the search field, and with Radu, we work on the project of the data lake. So let's move forward and let's see what is the INA. So the INA, INA, so you can see, stands for the Institut National de l'Audiovisuel, which translates into National Institute of Audiovisual. It is a French public institution responsible for preserving and promoting the country audio and video heritage. Indeed, the INA collects, archives, and makes available to the public a wide range of audiovisual material, including television programs, radio broadcasts, and newsreels. It is considered an important cultural and historical resource in France, providing access to the country media history and preserving it for the future generation, which is extremely important. In terms of equivalent organization abroad, the closest are the British Film Institute in the UK or the Library of the Congress in the US. So let's talk about numbers. INA's collection is the result of the archive of everything that is audio and visual broadcasted from more than 184 radio and television services in France, 24 hours on 24, every day since the beginning of 1990. If this can seem huge, this is just an aspect of the INA. As we can see, we have more than 22 million of hours of services recorded that generates over 1.1 billion views. And also we have photos. We have 1.2 million photos and up to 16,000 archived websites. So we can see the amount of data which represent for us a huge challenge, but also a really fertile terrain for the search engine's perspective. So as I was saying, the INA is just it's a very large institution. Our project is just a small part of it. So it covers every team, every project at the INA cover a different aspect of the process of, we can say, preservation of the media culture. So the project we work on is the data lake project. First of all, I want to credit the fathers of this project, so Gauthier, Colin, and Stanislas. Let's see what this is all about. So we have 60 million documents. We work with around 60 million documents. In this case, we are not talking about the content itself, but we are talking about the metadata. So everything that is behind this content. We are not dealing with for example, we are not dealing with music or with the video, with movie, but we're dealing with the information about this music or about the movie itself. Also, the data lake is extremely important to remember that as a 3 layers architecture, we have a storage part with different databases, so it's really heterogeneous. We can have SQL and NoSQL and Postgre or other type of databases. We have a middle layer where we have we can say the processing part, where we have a part where we update, transform, and synchronize our data, and then we have the management layer. That is the layer that interests us the most, as we have our search part. First, to understand our use case, we must describe our extremely complex data model. We have to distinguish 3 different aspects of our data. So we have the content, the event, and the media. Now, the content is unique. It can represent a video, a photo, or a text. The event instead represents a specific instance of the content. For example, if we take daily news is broadcasted every day. So the video of the daily news is the content. This can be broadcasted more times during the day, and it can be so associated at more events. And finally, we have the media, the third aspect of our data model. So where we do register our content. Can be a tape, a VHS, a Betacam, a file, an MP3, and MP4. Another extremely important aspect of our data model is, first of all, the separation between the content of them and the metadata. We all know the difference between what is the data itself and so the content. So it can be a video and the metadata behind it. So the description of the video itself, or the kind of format has been used to save it. But we have also a difference between the metadata themselves. So we can have, for example, free text, which is unorganized, unstructured data, and then we can have curated data. So another kind of, we can say, metadata with the types, description, concept, and names that is well-organized data, is well-organized metadata. So we can have metadata associated to different aspects so the different aspects of our data. So we can have metadata associated to the media, we can have metadata associated with the event, and we can have metadata associated with the concept. And this brings us to our graph, okay, that we can see here. This is only a part of it. Let's take an example. If we have an instance that can be a daily news, in the case of the daily news, we can have more events associated with the daily news. We can have some agent associated with the event. The agent can be the producer of the daily news in a certain moment. We can have as well credit annotations related to the instance. So it's extremely complex. It's as I said, it's only a part of our graph, and we have some challenges with that are brought from having such a huge and complex model. The first one is to fit all this into a relational database. So we can see we can have a fairly complex and large database schema with different tables, with different relations, and different keys. And also, it's really important is the transposition into JSON into a JSON document. Of course, we don't want this JSON document to be too big, to have too many fields, because it will be extremely hard to index all this in a normal amount of time, and also it will be hard to search for it. What was this were our challenge, and what was the first solution we came into, was to use the, we can say, the principle of divide et impera. So we decided to cut the schema in different parts, to split it in different parts. Each of them had a different view on different area of the graph, and we had a part for the concept, we had a part for the instances. So for example, we can have the part related to the instance will have information about the credit, the annotation. The part about the concept will have information about the text, the label, and then we have a part about the event. So we have let's say an index for each of each of separation that we made. But this was not enough, and I'll let Radu explain why.
Yeah, so thank you, Pietro, for introducing the data model, which really represents one of the key aspects of our project. Now I will briefly present the workflow that we defined for indexing these documents, which is basically a straightforward workflow from the sources of data, of metadata. We have the different sources and very heterogeneous, because some of them represent legacy databases, legacy relational databases that were built along the time. And then there are some transformations that are acted on top of this data in order to obtain a uniform and standard model for the whole collection. So there are some migration and curation actions that are performed by the stakeholders, by the users, archivists, to be able to complete the metadata associated to this large content. Everything is stored and centralized in a relational database. We have a PostgreSQL instance. And then the natural workflow would have been to insert all these documents into Elasticsearch. This is what we tried to do in the early beginning of the project. And considering the amount of data and the number of documents that we have, the whole process took around 2 or 3 weeks of indexing. So this was not considered acceptable because there are lots of updates to be added, and the data is continuously increasing, and we had to come up with a different implementation in order to speed up the indexing workflow. So our first optimization was the introduction of intermediary step. Basically, we perform the extraction of different relations in between the entities, and we create fragments, JSON fragments, that were temporarily stored into a document database in MongoDB instance. And then, based on a specific schema of these fragments, we decided to we defined indexing process directly into Elasticsearch documents. So in the two main actions that are specific in our indexing workflow was to optimize, in the first step, the SQL queries in PostgreSQL database, and also to define the flexible schema for the JSON fragments. So I'll get into more details related to the data model representations. So as we said, for each record of the relational database, we tried to associate fragments and JSON fragments. Here, if I take the example of an instance that contains texts, identifiers, or events and credits associated, The final JSON document that is sent to Elasticsearch will look like something that you can see on the right side of the screen, a rather flat document that integrates all the elements specified in the schema, but that can be exploited, and it can be easily indexed in Elasticsearch. If we zoom a bit into this notion of fragment schema, it's a method that is inspired from JQL. And it represents a declarative method to define the structure of the documents. So as I was mentioning, we can freely add or suppress parts of the schema according to what exactly we want to extract from the relational database. This gives us the flexibility to select part of the relation, so not the entirely graph of elements, and the implementation of the relation between entities is defined by this schema. So here on the right side, you can see that actually the schema can be defined at several levels. So it can be imbricated, and we can go deeper into different relations, different levels of imbrication. But we tried to keep this depth of relations quite low. So in order to keep the simplicity of the final documents. As a simple example of JSON fragment, so here I have only selected an instance that contains text, identifiers, and concepts. Each concept can have text and identifiers associated. So here you can see the result of JSON fragment containing the total list of text associated to each specific element. Just to illustrate the complexity that we could spare at indexing time, using these fragments, actually all these complex SQL queries are pre-computed, and the processing time during the indexation in Elasticsearch could be highly reduced. These fragments, they needed some transformation in order to be prepared to the final Elasticsearch documents. In order to do that, we used a JSLT transformation, which is an open source library implemented in Java. It's a transformation language for JSON, inspired by JQ, XPath, and XQuery. And in terms of performance, it's a very fast processor, and it's very easy to use and implement it without requiring full programming language skills. Moreover, different extensions, different functions can be added on the fly, and we used this JSLT transformation to produce the final JSON documents, to trim some redundant files, or to group or restructure different arrays of sub-elements. Just to illustrate the syntax and the way of we can declare different functions in JSLT. You have here some simple examples where you can define functions, loops on top of different arrays, or variables and different logical combinations or logic transformation on top of these fragments. So this brings us to the indexing jobs.
Yeah, so we have been talking about the data and the transformation. Now we talk about the indexation, which is extremely important as well, as we need an automatic way that help us to reduce our indexation time. We don't want indeed to start a process manually all the time. We have to index our document. So we have something that is called jobs. They can be asynchronous and asynchronous. We can start them with a call to our web service, or we can use a scheduler or watch folder system, also with a MQP messages queue. We have generic jobs that we parameterize using something that we call a task. Every task can contain something about the operation we have to perform. So, for example, it can contain the name of the index. It can contain the collection from where we want to get our data. It can have different parameters. So it's quite useful, as it allows us to make things automatically. Also, jobs are declared in a declarative way, defined in a declarative way, and it's really helpful, as it reduces a lot our maintenance efforts. Also, we have an orchestrator, which as we have some jobs that may trigger other jobs, and we need some sort of system that take care of all this flow. And also we can have the output of a job that can be the input of the following job. So we need something that takes care of all this. We have an extremely we decided to do all this. We decided to pick a framework which is called Talend, that allows us to do everything in an automatic manner. It's extremely we can see here the interface. It's extremely powerful, useful. We can use it. We have an extremely friendly interface which we can use to declare our job, to trigger them, to schedule them. And we can see on the below part, we can have the different parameters, like the Elasticsearch alias. So we have this interface that is extremely helpful. And we can pass to we can see how to define a job, what a job looks like. And this is really important. I mean, because to define a job, we don't need someone that knows how to code. We don't need someone that that has to code, essentially. But we have just pieces of the same. We have pieces of a job that we can reuse. So essentially, we have here our job. We can see on the upper part. This in this case is an asynchronous job. We can have we have in the upper part we are reading the different from a messages queue. We are setting up the different parameters. We have also a way to manage our errors, our warning. We have in the middle part, we check the Elasticsearch status. So we are checking if the index exists. Again, we have a way for checking our to see our logs and to generate some logs. And then we have in the indexation part, the part below, and we see that our documents are splitted. Our list of IDs are splitted into different lists, so we can index the different document in different bulk. And then we have a final part where we check the status. So we count the indexed document, we report the errors, and we update the alias. So as I was saying, this is extremely helpful, as it's easy to maintain and it's easy to create. I mean, we can see we have different parts here that are we can reuse, and we have generic jobs. We can easily parameterize them in base of the index we are using. So as we have many indexes, well, we have a single job that does care all of them.
So we talked about the indexation aspects. Now we'll present very briefly also the second part of the project, which relates to the search and the specificity of search functionalities and the way that we defined simple APIs. Our project provides a simplified view to the application layer, like simple full text search, different faceting, sort rules, etc. And this also preserve an abstract view on Elasticsearch query DSL, which is quite complex. So it's a way of keeping under the hood the complexity of Elasticsearch. It also allows to control the access to Elasticsearch cluster and to confine different rules of access. And we defined specific APIs, categories related to different functionalities for each index. We have get by ID, simple API, full text search, or advanced search, or even autocomplete functionality. And again, in order to build these APIs and to create the queries, we used the JSLT transformation to define, to build the Elasticsearch query starting from a very simple syntax. This helped also on the deployment and the maintenance of our APIs because we don't have to rebuild each time that a new functionality is created. Just to give you an example of the search API, on the left side of the screen, you can see a simple full text query that defines also a filter by date, an aggregation by event, and by different persons that are involved or associated to an event. And we define also a sort criteria. And on the right side, you can see the result of the transformation. What's very important to notice is that the 20 lines search query is transformed into almost 300 lines Elasticsearch query. So that shows that all the complexity of the Elasticsearch query can be covered and can be hidden by this API. Again, an illustration of the JSLT transformation, which is defined in small modules and generic methods that we can use and reuse in different parts of the search engine and different related to different indices. And this is something that it's done into a declarative fashion in the JSLT transformation. The workflow, it's very simple. It involves a first validation step, where we can select operators to be used, the language to be used in the query, pagination, and so on. The second part is the most complex, which is the query transformation in itself. To generate the Elasticsearch query using the filters, defining the aggregations or nested aggregations, defining different user profiles, and so on. And finally, the third part, it's still a transformation that allows us to present the result of the query in a more concise fashion, and that allows us to extract snippets from the search results. All these APIs, they fit into a general architecture that we show it here. On the right top of the screen is the application that interacts with our search API, and all these transformation and the query interpretation is done by a small Spring Boot applications developed, deployed on Kubernetes cluster. So very easy to deploy and to spin on new instances. The Elasticsearch cluster interacts over HTTPS with the Kubernetes cluster. It's an on-premise Elasticsearch cluster, and the search API are very simple and light API to communicate with the search engine. We have also a controller proxy where we load the overall definitions of the APIs. Just to finish, a couple of words on the evaluation that we performed. We managed to index more than 50 million documents in less than 2 days. So that showed us, that proved us that the JSON fragments optimization divided by 10, the global processing time, and we performed some evaluation on the search, the response time of the search using the NeoLoad platform. We use different complexities of the queries using different nested aggregations and filters and so on. This is a snapshot of NeoLoad evaluation. The main thing to observe here is the response time that was maintained steady in between 20 and 50 milliseconds, and independently on the increasing number of users. We started with 80 users and we scaled up to 400 users. To conclude, there are several points that are required some thinking and some optimizations on our side. First of all is the data model that we used, and here is the idea of the entities graph and the split of this graph based on functional views. The second major benefit, it was related to the usage of the fragments, the JSON fragments that optimized the overall indexing process. The third point to recall is the JSLT transformations that helped us on the normalization of the document, but as well on the query implementation. The search API that is used at the application layer, and the last but not the least, the search relevance, that it's an ongoing work. Thank you, and I'm looking forward for your questions, eventually online or offline. Thank you.